All right, you should be able to see my screen. I'm Michael Abraham, as Frank mentioned, and I've been on CXL for the last several years. I've enjoyed watching it grow as from a spec to actually working on getting some products out in the market and getting them shipping. So we're going to spend a little bit of time talking about what Micron's doing today on the memory module front, and we'll have a little bit of time for some questions at the end. So today's focus is really to take a look at what we see, part of how we see the data center challenges that CXL is addressing. Um, we're focused on this right now as a memory module perspective. There, we recognize, given Arvind's presentation, that there are a multifaceted approach to how we're looking at this in industry. And while true, we want to make sure we get stuff moving pretty quickly into industry and be able to really prove the value proposition of CXL and be able to see how it transitions and disrupts data centers going forward. We'll spend a little bit of time talking about memory storage hierarchy, about the memory module that Micron's been working on for the last little bit. And then we'll look at two use cases that we've got some measurements on. There's one of them is database related, TPC-H, and then the other one is around AI inferencing, and then talk about how to get involved. All right, so when we look at where we're headed with data center, AI is definitely something that is on everybody's mind, and also a lot of the databases that we see out there. There are several options for when we run out of memory. If we run out of memory, essentially we need higher capacity for in-memory databases, some of the software as a service, and AI training and inference. And we are seeing quite a wide variety of ways to get that memory into the system, into the data centers. That result, though, is fundamentally we do see as higher capacity demand. We see a lot of times where we just can't get enough, and so oftentimes we'll add 2 CPUs to a socket or to a server and to be able to make that happen, or we scale up and add in multiple servers as well to be able to meet the memory demand. And so the question is there a way that we can essentially provide that memory capacity, and especially as core counts grow up, to be able to have more memory per core? Bandwidth is the other aspect of what we're seeing here. We are seeing a lot of real-time data analytics that take place that do require quite a bit more, especially as we have more processor cores. We are also seeing that essentially we need to be able to have more bandwidth per core. And the question is, how do you get that? We're scaling, of course, DRAM speeds as fast as we can, but there is a possibility of also using CXL to help provide that additional bandwidth there. And then finally, lower data center TCO. If we look at where things are headed in the data center, we see that oftentimes it's handled in a binary form. So for example, we might add a lot more DRAM in, but we typically optimize that for every single socket. And in the case of wanting to avoid stranded memory or having too much, in some applications, memory per server, there is some benefit as well for CXL to be able to provide a unique amount per server of additional memory that can help address the minute need, in some cases surgically almost, of extra capacity or bandwidth based on what the workloads are requiring. All right, so if we were to compare and look at how the storage hierarchy works between memory and storage, the very top we have our absolutely fastest memory, the lowest latency. HBM today is one that's especially getting prevalent in the AI space and getting used there. Provides an incredible amount of bandwidth based on the location of where it is and right next to compute engines. DDR memory is the workhorse, I'd say, overall of the industry, and in some cases we're basically seeing that particular case where there's additional demand even with the HBM and DDR for higher bandwidth and higher capacity. By the time, though, we get to storage, we've got a little bit of a problem that as we move down this hierarchy, we essentially are increasing latency. We do have extra capacity, but it takes extra amount of time to get that data up into the next to the CPU in the memory space. And so that's one of the benefits essentially that CXL is providing is it helps bridge that gap. It provides the additional memory capacity. It's basically byte addressable, and then it also provides additional bandwidth expansion as well. So one of the benefits is that essentially you have to go to storage less um, in order to feed the data that you need to your CPU, and that overall, as you have more CPU accessible memory, it actually can speed up workloads, including the applications that we run on top. All right, so for Micron, we've introduced this last July-August timeframe the CZ120. It is our first foray into the CXL market. We've are we've done this with two capacities of products. So we have one that's 128 gigabytes of additional capacity per module, and the other one is 256 gigabytes of capacity per module. And when you put 8 of those into a server, we have the ability with the 256 to support essentially an additional 2 terabytes of incremental memory capacity. And then speaking of the TCO workload aspect of it, one of the additional benefits is you put in as much as you need up to this maximum essentially. So this is potentially per socket. So if you have a multi-socket server, you could potentially even add more memory per server. All right, from the bandwidth side, we are seeing as well, measured with MLC tool that Intel provides on a 12-channel server with 4,800 megatransfer per second RDIMMs or DRAM modules. We're essentially seeing a 34% increased server memory bandwidth. And this particular product uses PCIe Gen 5, which is currently the latest and greatest to be able to provide that extra bandwidth. And so it's is running the 36 gigabyte per second is pretty close to the theoretical bandwidth of what we can effectively achieve for a 70-30 workload, 70% read, 30% write. And then in terms of form factors, how do we get this into servers and how do we make use of it? There are a couple ways to do that. We've seen some add-in card deployments, but in particular for the ability to deploy easily and for the ability to do hot plug operations, we're using the E3S 2T form factor defined by SNIA. And unlike an NVMe SSD, which typically uses a by 4 width of and a PCIe width of by 4 lanes, we're using an 8-lane interface that doubles the bandwidth on top of that as well, which is well suited for the almost 10x performance that we see in bandwidth for a memory module as opposed to an SSD. All right, so how does this actually impact real-world performance? So if we use TPC-H, which is basically looking at Microsoft SQL performance, we are seeing that as we increase the number of streams of operation between a DRAM-only solution that's the servers based on 12 RDIMMs at 64 gigabytes, we're showing a 23% improvement just for a single stream. And then as we add more streams to that to 8 and 20, we're seeing a significantly higher multiplier that goes along with that. Basically, with 8 streams, we almost double the amount of performance from the query counts that we're able to achieve in that same amount of time. And for 20 streams, we're over 200% better, essentially. And if you look at it a slightly different way, we've got we're all about memory at Micron. So we've got a look at both the 64 gigabyte and the brand new 96 gigabyte RDIMMs that we announced just this last year. And if we look at the DRAM only performance here with the 64 gigabyte, we do see, of course, we're recommending a 96 gigabyte RDIMM for greater performance. And part of this is when we look at this, we're just able to put more data into the memory from a DRAM only standpoint, which then reduces need to go to disk and it overall shows an application performance increase. But even with that, when we add in the CXL with both the 64 gigabyte and with a 96 gigabyte RDIMM, we see continued improvement in the overall operation the number of queries essentially handled in the same amount of time. And so you see that this scales actually fairly nicely, somewhere in that 16 to 20 stream. We're at at least a 60% improvement over with a smaller RDIM size, even a little better with the bigger one. And then we seem to maintain that fairly well through 24 streams. And when we get to beyond 24, we show the really good performance against the 96 gigabyte RDIMMs. All right, looking at the AI side of the house, there's a couple things to kind of take away from this one. So we have two ways to look at it. There's if we look at max bandwidth, this is oftentimes the AI is a very much a bandwidth limited thing. And so if you have a DRAM only solution, typically you're filling it with a bunch of RDIMMs, and then we have the ability to add CXL directly into that processor as well. So what we're seeing as we look at the read percentages anywhere from 0 to 100%, that we have a little bit of a beautiful sweet spot here in that 50 to 80% read percentage range, and which is great. In some cases, we're showing 50%, almost a 50% improvement, 30 to 40% improvement in this window from just a raw bandwidth multiplier standpoint. And then what does this actually do in terms of translating this into a final workload? Well, with a large language model using Llama runtime, essentially, we are seeing that we are able to reduce the runtime of a query, and in this particular case, it translates into an additional increase in the number of tokens per second that can be processed. And in this particular example, where we're looking at DRAM only, and then we were looking at DRAM plus CXL memory modules. We're seeing over about 11 to 13% increase at the application level after it's all done. And this is just based on a very overall small language model compared to what could be possible. All right, so we've got a lot of work that's going on internally, and then also with many of our partners at improving the overall ecosystem around CXL. We do have additional workloads that we're evaluating in-house and working through those details. And we'll have more to announce in the future going forward. But to get involved, we would love for you to have an opportunity to take a look at the Micron CZ120 modules, to be able to use them in-house, to put them on your workloads, and to get everything ready for deployment in the future. So we have at micron.com an opportunity /CXL, an opportunity to be able to look at our servers, or excuse me, our memory modules. You have the ability to get the documentation around them, including data sheets, the thermal models, electrical as well. Look at signal integrity, other issues, and we would be happy to work with you on that. So we'd encourage you to go to micron.com/CXL, look at our technology enablement program, TEP, and have an opportunity to collaborate on what you're working on. So with that, I've got a little bit of time for some Q&A, and let's see if I can figure out where it's hiding here. Here we go.